Hello everyone, I am Ivan Tkachenko, student of Technical University of Košice, and in this video I want to tell about my experience using reinforcement learning, specifically deep reinforcement learning in my robotics navigation project. So, some basic information about reinforcement learning before we start. Reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with an environment. The agent learns to achieve a goal or maximize cumulative reward by taking actions in the environment. In reinforcement learning, the agent learns through trial and error, receiving feedback in the form of rewards or penalties based on the action it takes. First, I wanted to tell some key components that will be useful for us further in this video. That agent is the learner or decision maker that interacts with an environment. Environment is the external system with which the agent interacts. Actions are possible moves or decisions that the agent can make. State is the current situation or configuration in the environment. Reward is the numeric feedback from the environment to indicate how good or bad the actions were. Policy is the strategy or rule that the agent uses to select actions based on different states. So, now when you know more about reinforcement learning, I can tell you more about our project. The main objective of our project was to make robot navigate, move, and avoid static and dynamic obstacles in simulated environment. And after some research, we understood that this task can be solved by reinforcement learning. But there was one problem. The most conventional approach in the reinforcement learning is using QTable. But we quickly understood that this won't work in our case, because QTable works very well when you have specific limited number of states that are possible for your agent. For example, some 5x5 field of cells, and the state of the agent is represented by x and y of the cell in the environment. This way you can only have 25 possible states. But for our task we had simulated an environment where only the position of the robot is represented by the real numbers. And also we wanted to use much more different sensors, and the outputs of those sensors are also represented by the real numbers. So this way we could have the millions of possible states which just absolutely won't work with the conventional QTable. So for our task we chose to use deep reinforcement learning, specifically deep Q-network algorithm. So deep reinforcement learning is just the combination of reinforcement learning and deep neural networks. Deep neural networks in this case are used to approximate the functions that traditional reinforcement learning algorithms seek to learn, such as the value function or the policy. Now let's move to the environment and the agent. Environment is represented by simulated map. We had a bunch of maps with different combination of static and dynamic obstacles, different difficulty levels and targets that robot has to reach. Here you can see some of the maps. You can see there are two maps with only static obstacles and one map that contains static obstacles and dynamic. Dynamic obstacles are the blue ones. Also, green dots are the targets that robot has to reach, and different obstacles are mainly represented by some gray or black objects. And our agent is a robot that has lots of different sensors, for example, distance sensors, compass, GPS and bump sensors. All the numeric information from those sensors is used as a state. On those images you can see the robot, our agent, that has different sensors. It looks kind of funny because this robot is from the simulator. So our state looks something like that. We use x and y coordinates from the GPS, angular deviation from the target we get from the compass, 5 values from distance sensors, and also one value that shows if robot is colliding with any object right now. Also our DQN can choose from 3 possible actions: move forward, turn left, or turn right. Now I want to tell more about our neural network. On this image you can see our neural network topology. It has input size of 9, because our state has 9 elements. Also it has 2 hidden layers, one with 156 neurons and the other with 78 neurons. Between all those layers are ReLU activation functions, and also network has 3 possible outputs, our 3 actions: moving forward, turning left, or turning right. So network receives current state of the robot and decides what action to take. After choosing action, robot moves and the state changes. And based on the new state, reward function gives reward for the network. We have a complex reward function, but basically we give small rewards if robot turns closer to the target, moves closer to the target, and a very big reward if it reaches the target. Also, if robot gets closer to the obstacles, reward becomes exponentially smaller. And if robot collides with the obstacle, it receives big penalty. Also, we give our networks a specific limit of steps in which robot must reach the target. If robot takes longer to reach the target, it receives very big penalty. Limit of steps gets smaller with time. We made it so to make robot optimize its way of reaching the target and to encourage it getting to the target faster and faster in each episode. So, using states and rewards, our network forms a policy to navigate robot in the environment. Our models were mostly trained for 1 or 1.5 hours. Now I just wanted to show some of the results of our models. Here you see a robot in the medium difficulty environment with obstacles of different sizes. You can see that it moves from one target to other and tries to avoid different obstacles in its way. Also, all those records with results are sped up nearly 5 times, so really in the simulation it was a little slower process than on those videos, even though even on those sped up videos it also looks like a very slow process. But I think that possibly with bigger computational power you could speed up the simulation much more and also reach much better results with those models. So in this scenario you can see robot navigating through static and dynamic objects, and that it still has some problems with dynamic obstacles. It just could not choose in which direction to go in time, so he's run out of time and went to another target. And now he has even more problems with dynamic objects. So, in conclusion, our model can effectively navigate in the environment with static obstacles, but still has some problems in scenarios with dynamic obstacles. But I believe that our results are important for further research in this field, because we've shown that it is possible to not only test but to train a successful model in this simulator. We believe that deep reinforcement learning is an effective and promising method to solve navigation and obstacle avoidance problems. There are lots of ways to improve our project that are described in our article. Some of them are to try use full field of view leader, or to use bigger model with a better computational power. So in the end, I think that deep reinforcement learning and DQN are very promising methods to solve problems like navigation. And those methods are really easy enough to use if you have good computational powers. and I think that the information in this video could have given you at least some basic understanding of reinforcement learning and how you can try to use it in your own project. Thanks for the attention.